All right, continuing on here with class number 8. Here are some examples. All right, so here is example from problem 5.1 and 5.5 from the textbook. So we have a condition where we have 100 megapascals in tension in the x direction and negative 75 megapascals of shear, which means it's on the positive x face in the negative y direction. So here is our stress state. We can draw a Mohr circle, a 3D Mohr circle here of this, and get the principal stresses. I don't show it here, but I'm sure you can do this. So we have 140.1 megapascals in tension for sigma A and 40.14 megapascals in compression for sigma B. And so if we want to, we can put them in order, sigma 2 being 0 as we see on the diagram. The absolute maximum shear is sigma 1 minus sigma 3 over 2. In this case, it's also going to be equal to the radius because we have the condition where we have the outer circle right here. Right here is the one that we're really looking at right here, because the uniaxial case happens right here, but that's R right there. So also it's going to be equal to the abs max. So for now we can also do von Mises. So we'll wait a second before we do our maximum shear stress theory safety factor, although we could do it just right now. For von Mises, this is a uniaxial case, so we just have to put in the original stresses. Excuse me, I went too far. Also, by the way, it should say, okay, there's going to be our yield strength that we're going to use here. Okay, so we get the von Mises stress of 263.9. Now we do the most important thing, which is to find the safety factors. First, the maximum shear stress theory is just the yield strength, or the 350 divided by 2, to make it into a shear yield strength, and then divide that by the abs max, and we get a 1.94. And now we just have to compare the von Mises stress and the yield strength. And you can see that we have a slightly larger value of our safety factor. This is an important thing to note, that you will they'll either be, in some limited situations, the safety factor, maximum shear stress theory, and distortion energy theory, they could be equal to each other, but most often distortion energy theory is going to have a larger safety factor. It's more of an accurate portrayal of what the stress state is, whereas maximum shear stress theory is more of a conservative approach. And it looks a lot easier to understand when you put it onto a stress yield envelope. Of course, the ellipse is distortion energy theory, and the 6-sided hexagon thing is maximum shear stress theory. So we plot our point right here of our sigma A and our sigma B. Now remember that sigma A was a positive value and sigma B is a negative value, which puts us down into this quadrant. If we extend the line and we label points O, A, let me get this out of the way, B is going to be where the line extends, and then B is where it intersects maximum shear stress theory. C is where it intersects the envelope for distortion energy theory. And we could graphically compare the results here, and the ratio of the lengths should coincide with what we found from the equations for the safety factor. So I'll take a look at OA, and I take a look at OB, and then also measure OC. And so the ratio of OB to OA is the maximum shear stress theory. That is the how much further are we from yielding. So that's what we're measuring. And then for distortion energy theory, it's going to be OC divided by OA. So we could do, and by the way, we're going to do this for various other things too, where we could solve this by equation, or we can also, and we can confirm it graphically. It gives us sort of a better understanding of where we stand. I would note that, like, if you had pure shear, it is a 45-degree angle right there that we could prove to ourselves by way of like right right here would be the shear points where we would plot onto a face. So the Mohr circle would look like this, where we had sigma A right there and sigma B there, and they'd be equal to each other, except sigma A would be positive and sigma B would be negative, and so that's why it would be a straight line that's diagonal in that lower quadrant. So kind of an idea of where we stand, and we could also see there, right there is a graphical portrayal of why one is a larger than the other. Why distortion energy theory is larger than maximum shear stress theory, because it's on the outside. All right, so here is another example. This one has compression and compression, and a shear of 50, and they're in megapascals again, and we still have that 350. All right, so I think I came up with this example. Did I? Yeah, I think I did. All right, so let's get a Mohr circle all plotted out. So here we have a condition where here's our main Mohr circle from plotting the faces are right over there. And we can see here's where we're going to have our maximum shear for this stress state. So our principal stresses end up being both compressive, which makes sense, right? Right here and right here. And if we put them in order, sigma 1's 0, sigma 2's compressive 169, and sigma 3 is compressive 281, we'll say. We want to find absolute maximum shear right here. That's going to be sigma 1 minus sigma 3, but remember we have a minus minus, so it ends up being that 140.5. So the von Mises, because we do not have uniaxial stress, we can't use that easier equation. We must have both of those in there. But here's where we want to make sure we're playing with the negatives right. We have a negative right there from the equation, but we have a negative in there. So it overall ends up being a negative. And then, of course, it's squared here, so that doesn't matter. It's squared right here. So when you're done with that, we have a von Mises stress of 244.9. And now when we go to safety factors, you could see that we take that 350 divided by 2, we get a 1.25. And then distortion energy theory, we have a slightly larger 1.43. And then if we plot them, you can see we're down here in the third quadrant, and we can extend, we can label these points O, A, B, and C, and we can get these lengths, and we can kind of see where we are, right, with respect to that. We could see how these ratios worked out, how these values, I should say, can compare with each other in a graphical sense. So here's another example. Well, maybe I'll stop here and we'll do this in another video. Yeah, that's all I'll do. So come back for more.